Hello, welcome. In this lecture, we are going to introduce two more unit vectors along with the unit tangent vector. At a given point on a smooth space curve described by the vector function r of t, there are many vectors that are orthogonal to the unit tangent vector t. We single out one. Recall that the vector t prime is orthogonal to t. This follows from the fact that the dot product of the unit tangent vector with itself equals to the square of the magnitude of the unit tangent vector, which is equal to 1. Now, differentiating both sides with respect to t, we obtain t prime dot t plus t dot t prime equals to the scalar 0. Now, since dot product commutes, we can write t dot t prime as t prime dot t. So we have two terms of t prime dot t. Therefore, we have this equation. And then, by cancelling the factor 2 from the left-hand side, we obtain the equation t prime dot t equals to 0. This shows that t prime is orthogonal to the vector t. Generally, the derivative of the unit tangent vector is not a unit vector, but any point where the curvature is not 0, we can define the principal unit normal vector denoted by n of t, or simply called the unit normal by the equation shown in 6.1.1. So, the unit normal vector is defined to be equal to the derivative of the tangent vector divided by its magnitude. Note that the unit normal is perpendicular to the vector t. Since n, the unit normal vector, is parallel to the derivative of the unit tangent vector, but the unit tangent vector is perpendicular to the derivative of the unit tangent vector. So n must be perpendicular to the unit tangent vector t. And we will see that the unit normal vector as indicating the direction in which the curve is turning at each point. Let's see an example. Find the unit normal vector for a circle of radius a. Let's have a look at the solution. A circle of radius a can be described by the following vector function. R of t equals the vector whose components are a cosine of t and a sine of t. Therefore, the derivative of the vector function has components negative a sine of t and a cosine of t. So the unit tangent vector is given by this vector, whose components are negative sine of t and cosine of t. So the derivative of the unit tangent vector has components negative cosine of t and negative sine of t. As defined, the unit normal vector is given by this equation, which is this vector. Can also be written as negative of 1 over a times the position vector r of t. This equation shows that the unit normal vector is parallel to the position vector, but in the opposite direction to the position vector. As shown in the following figure. At any point on the circle, the tangent vector is shown in the blue color and the normal vector is shown in the red color, which is acting toward the center, exactly opposite to the direction of the position vector of the point A. Let's have a look at an animation. Now we can define another vector called the binormal vector, denoted by the symbol b, by the equation shown in 6.1.2. So the binormal vector b is defined to be equal to the cross product of the tangent vector with the unit normal vector at any point on the smooth curve. This vector b is orthogonal to both the unit tangent vector and unit normal. Also, observe that the magnitude of the binormal vector is equal to 1, since the magnitude of the binormal vector is the magnitude of the cross product of the unit tangent vector with the unit normal vector, which can be written as the product of the magnitudes of the unit tangent vector and the unit normal vector, and the sine of the angle between the unit tangent vector t and the unit normal n. So the unit tangent vector has magnitude 1 and the unit normal has magnitude 1, and sine of 90 degrees is also 1. So this gives the magnitude of the binormal vector equals to 1. In general, the vectors t, n, and b, starting at the various points on a curve, form a set of orthogonal vectors, like the standard basis vectors I, j, and k, called the T and B frame, that moves along the curve as t varies. This TNB frame plays an important role in the branch of mathematics known as differential geometry. Let's see another example. Find the unit normal and binormal vectors for the circular helix, given by the vector function r of t equals to cosine of ti plus sine of tj plus t times k. Let's have a look at the solution. We first need to calculate the required quantities to compute the unit normal and binormal vectors. So we have the vector r prime as negative sine of ti plus cosine of tj plus k, which is obtained by differentiating the component functions of the vector function r. Then, by definition, the unit tangent vector is given by this formula, which gives us this vector. And then the derivative of the unit tangent vector is the vector with components negative cosine of t over square root of 2 and negative sine of t over square root of 2. In other words, 1 over square root of 2 times minus cosine of ti minus sine of tj. Therefore, the magnitude of the derivative of t is 1 over square root of 2. So, the unit normal vector is given by, which is equal to negative cosine of ti minus sine of tj, or the three-dimensional vector with components negative cosine of t, negative sine of t, and 0. This shows that the normal vector at any point on the helix is horizontal, since the z component of the vector is 0 and points toward the z-axis. Now, the binormal vector is given by which is the vector with components sine of t over square root of 2, comma, negative cosine of t over square root of 2, comma, 1 over square root of 2, or the vector shown here. The unit tangent vector t, the normal vector n, and the binormal vector b for a circular helix at a certain point is shown in this figure. The plane determined by the normal and binormal vectors n and b at a point P on a curve C is called the normal plane of C at that point. It consists of all lines that are orthogonal to the tangent vector t. The plane determined by the vectors, the unit tangent vector t and the unit normal n, is called the osculating plane of C at P. Please see the notes for the details.